So we get lots and 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 lots of options for how we can write a logarithm. And I talked about how there's really only two that are particularly good. There are only two particularly useful logarithms. There are two that we really focus a lot of our things on. It's disrespectful to say that there are only two that are useful, but there are two in particular that we get the most use out of: the natural logarithm and the common logarithm. However, e and 10 aren't the only numbers we'd ever take the powers of. So it's nice that we have another thing here called the change of base property that allows us to say the logarithm base b of some value m can be written in terms of a new base a by saying that this is equal to the logarithm of base a of m divided by the logarithm base a of b. So in particular, if we want to deal with common logarithms and natural logarithms, we could say that for any base b, the logarithm base b of m is equal to the log base 10 of m over the log base 10 of b, or the logarithm base b of m is log base e, that is the natural logarithm of m, over log b of e. And this result here is actually fairly easy to prove, that if we take our pieces here and we let y equal log base b of m, so something like this is equal to y, then we have m is equal to b raised to the power y. That's just our basic inverse relationship at play there. If we take both sides of this term here, m equals b raised to the power y, excuse me, I need to give myself just a tiny bit more space here. But if we take that term there and evaluate it in terms of the logarithm base a, so we take log base a of m, that's going to be equal to log base a of b raised to the power y, then we're still going to have log base a of m. Meanwhile, over here we can use the power rule, bring down the y. We have log base a of b, and then we have that b is equal to log base b of m, so log base a of m is equal to log base b of m times log base a of b. And then from there we can recognize we actually have all three of our parts for that relationship there, where if I divide out log base a of b, that would give me log base a of m over log base a of b is equal to log base b of m. So that's why our rule here works. It's essentially just a subtle and recycled use of the defining relationship of logarithms. You can always rewrite in terms of a new logarithm base, just in terms of that extra piece of division there. So if we have something like log base 5 of e cubed, yeah, we could pull out the 3 and get log base 5 of e, but log base 5 of e, not super nice, and it's not the sort of thing that's easy to find on the calculator. Instead, we could use the change of base formula there and say that this is equal to the natural logarithm of the value on the inside, natural log of e cubed, which is a much more natural thing. That would just be equal to 3. While on the bottom, we're stuck with a less helpful thing, but it's just the natural log of 5. And remember, the natural logarithm is a really nice one. We haven't seen so much of how it's used yet. We'll get more of that at the end of the chapter, but it is something that's very convenient to work with. It has lots of natural properties, and in particular, just about every calculator that's more advanced than a dollar store one will have the natural logarithm built in. So, if you need to approximate, this is a lot nicer. And as we see more uses for the natural logarithm, we'll understand why you'd want to be using this guy more often generally. Anyway, we can get our value there is about 1.864. For our purposes, though, if I asked you to do stuff with change of bases, I'd probably want this instead, because it shows you know how to use the formula, and I'm more interested in seeing you know how to use the formula than you know how to use a calculator. Anyway, that's all we have here for 4.3, just introducing our main properties of logarithms in terms of their algebra. So 4.4 is going to be all about applying them to the process of solving exponential and logarithmic equations. That is, equations that have exponents or logarithms in them. let's get in there and work on that too.